Hi everyone, my name is Zhang. I'm from the Chinese University of Hong Kong. Today's my presentation is parallel query processing to separate communication from computation. Here is the tables of contents. First, we'd like to talk about the background. The parallel query processing denotes the process of the transformation of high-level queries, such as the circle query, into execution plans that can be efficiently executed in parallel and the execution of such plans. In this talk, we focus on reducing the communication cost of parallel query processing in distributed environments. On the right, you can see that a query T join S join Rs goes through the logical optimizations and the physical optimizations and get the final execution plan. In existing systems, to enable parallel execution, it is common to adopt the exchange operator model style parallelism to implicitly parallelize each individual relational algebra operators, such as join, aggregate, and etc. Each parallel relational algebra operators is in one unit and cannot be separated and consists of implicitly communication and computation steps. On the right, we can see that for a hash join, we can parallelize it into the shuffled hash join, which consists of communication and computation. In existing system, for such an optimized execution plan, the execution sequence will be we first does the communication of the SHJ, then we does the computation of SHJ, then we does the communication of SSMJ, then we does the computation of SSMJ. We can see that the optimizer largely optimizes the query with regard to relational algebra operators without realizing the distributed environment doing the logical optimizations, and relies on the parallelized relational algebra operator to enable parallel query processing during the physical optimization. The communication and the computation are tightly coupled inside each parallelized relational algebra operators, and the computation must be done immediately after the communication. As a result, we can see that the potential very large computation results of the SHJ must be communicated immediately by the SSMJ, with little room to optimize. Next, we show how can we solve such limitations. To solve the limitation of the parallel query processing by the existing parallelization methods, we explicitly separate communication from computations for relational algebra operators, such as select, project, join. By separating communication from computation explicitly, we make it possible to move the communication inside the relational algebra operator in a flexible way. We use an example, R join S, to illustrate the new operators that enable us to explicitly separate communication from computation. The first operator is the partition operators. It partitions the relations by a hash function HB, which partitions based on the values on attribute HBs. And in the bottom, you can see that the relation R and the relation S are partitioned by the functions. Next, we introduce the pair operators, which pairs the partitions of R with the partition of S, if they can be joined, and generate the pairs of partition of R and S. Next, we introduce the local computation. In here is the join. Perform the local join of the partitions Ri join Sj over the pairs Ri and Sj. Finally, we merge the partitions R, I join SJs, all of them into a single relation. This operation can be done purely logically without incurring any cost if it is done in the distributed system, as we can just logically see them as being a single relation. All in all, we can see that with new operators, we can explicitly define the communication and the computation in relational algebra operators. Next, with the new operators, we can move the communication and computations in a more flexible ways. In the bottom, we have an example. First, for the optimize the logical plan of the query R join S join T, we can separate its operators into pure communication and computation operators, where the communication operators is marked blue and the computation operator is marked orange. Then, after we're doing this, we can push the communication operator, which is the partition HC down to the position that is the HBC. Note that we can do so because that it is okay to do final partitions at an early stage without changing the results. Next, after we have done the partition push down, we can push up the computation of join 2. And in this ways, we delay the computation of the join 2. It can be seen that by performing the communication push down and the computation push down, we can move the communication in a very flexible way, which can greatly reduce the communication cost of the operators that probably will generate large intermediate results by delaying its computation and bring forward other communications. All in all, here that we propose the operator level separations that separate operators into the combinations of merge, partition pair, and the local computations. And also we propose the algebra level reorders that enable us to move the communication and computations in a more flexible ways. Also, we prove that such separation and reordering is generally applicable to select, project, join, Cartesian product, set union, set difference, aggregate. Next, we show how we build the system around the separation. The system is called SQL that is built on the Spark. Next, we highlight the main difference of SQL from the existing systems. First, for the query optimization, we propose a two-stage optimizers that it will first find the optimal plan in the relational algebra search space first. Then it will separate the communication from computation for the relational algebra operators and reorder the communication and computations in the new search space. By doing so, we ensure the compatibility with the existing optimizer and reduce the search cost. Also, for finding the optimal plan for reordering communication and computation, we propose several algorithms, which includes a rule-based algorithm, a greedy algorithm, and a dynamic programming-based algorithm. For the planner, which is responsible for convert the optimized logical plan into the actual physical plans, as we have explicitly separated the communication from computations, it enables us to optimize the communication and computation in a final ways. First is that we propose the new rules for optimize multiple pair operators into a single motivation pair operators that reduce the unnecessary communication. The second is that we propose a new rule for finding the optimal hash functions for the partition function. Next, we propose new rules for pushing down the pre-processing part of the computation steps past the communication. Then, for the physical operators, we have implement an efficient multi-way shuffles on the spot that actually avoids the expensive shuffle process and directly move the partitions across the cluster. And also, we have implement an efficient local multi-way join and enable pipelining of the multi-way join with other previous relational algebra operators on the spot. Okay, next part, we talk about the experiment. In the experiment, we compare our systems with 6 different systems that are from different domains. Also, we have tested our systems under 30 queries that can be grouped into 5 workload groups. And also, we have tested our systems under 10 datasets. First, we show an experiment that compares our systems under different workloads. In this experiment, we test the code under the workload that have different selectivities. That will have low selectivity, which means that all the joins will have low selectivity, and the low high selectivity, which means that some of the join will have low selectivity and some will have high selectivity. And the high selectivity workload, that all the join will have high selectivities. And also we test under different join forms. For example, we test it under star join form, snowflake join form, line join form, tree join form, and cycle join forms. And from the graph, we can see that the school can greatly reduce the numbers of tuple shuffled if the workload generates large intermediate results. Also, we can see that the school does not deteriorate performance on workload with small intermediate results, such as the workload that with low selectivities. And we can see that for the hypercube join, although it can perform good under the high selectivity workload, it deteriorates the performance under the low selectivity workload. Next, we show that our systems in a real workload, that is subgraph query workload, and compare it with existing systems. The subgraph query workload, it will generate very large intermediate result, so that the school can greatly reduce execution time on such queries, and it can outperform the existing methods up to 3 orders of magnitude. For more experiments, please refer to our paper. Now, here is the takeaway that we can see that the existing parallelized operators tightly couple the communication and computations in one operators, and the existing optimizers are largely unaware of the underlying communication and computation due to the ways that the existing parallelization works. In our work, we further separate relational algebra operators into explicitly pure communication and pure computation operators. By doing so, the communication and computations can be moved in a more flexible ways once they are separated. And in the experiment, we can see that the school has large advantages on workload with large intermediate results, while the performance does not degenerate on the other workloads that may have not that much intermediate results. Also, the school is open source at the GitHub, and the link is shown below. Thank you for listening. Do you have any questions?